Imagine you have a database containing all reviews on, say, an e-commerce site. And given those reviews, you'd like to generate relevant product recommendations for users of the site. Such an application, like many others in domains ranging from data analytics and machine learning to science and engineering, can be expressed mathematically in tensor algebra by representing your data as a tensor, which is essentially a multidimensional array. Now, as we can see in this example, tensors that represent real-world data are often very sparse, meaning that most of their elements are zeros. But often they're also much too large for every element to be stored in memory. So to be able to store such sparse tensors without needing, say, a whole data center, we have to store them in some specialized format that compresses out the zero elements. And over the past several decades, many formats have been proposed for efficiently storing sparse tensors in memory. Here we can see just a few examples of these formats. And many of them are widely used in practice because they all have to make different trade-offs, so none is ideal in every respect. Some formats, for instance, make it more efficient to insert new nonzeros into a tensor. Others, meanwhile, are optimized for reducing the memory footprint of tensors that are used in structured stencil computations or in mesh simulations, for instance. What this means is that choosing the right format to store your sparse tensor is critical for achieving good performance. To illustrate this, let's say we have a very simple application that just performs two operations. First, the application takes some raw data, and from that, constructs a tensor that represents the data. Then, the application will perform some computation with the tensor it constructed earlier. Now, one option is to simply store the tensor as a list of its nonzeros along with their coordinates in the coordinate format. As an alternative though, we can instead store the tensor in dia, for instance, which uses a compression scheme that avoids explicitly storing the coordinates of each nonzero. As we can see, this lets dia greatly reduce memory traffic at runtime and thus significantly speeds up the compute step. However, because of the way it compresses out nonzeros, constructing a tensor in dia requires making multiple passes over the raw data in order to figure out how much memory to allocate beforehand, and this significantly slows down the construction step. So what this shows is that different formats are suited to different operations, and thus to optimize the overall performance of an application, we have to use the most appropriate format to store the tensor for each operation. Now this of course doesn't come for free, since at some point we have to convert the tensor that we constructed in the coordinate format to dia. Though if this conversion is done efficiently, then the overhead might still be worth it. The problem though is that performing this conversion efficiently is often difficult to do in practice, even with hand-optimized libraries. And this is because the number of possible combinations of source and target formats grows quadratically in the number of supported formats. And efficiently converting between each combination of formats requires very different and complex code. So for widely used libraries like SparseKit that supports tens of formats, it's simply impractical to implement efficient code for every possible combination. So instead, what handwritten libraries would typically do is to just pick some arbitrary format and only implement efficient routines to convert tensors to and from that selected format. Now this approach does make it possible to convert between every combination of formats, though for most combinations, such as coordinate to dia in this case, one will actually have to perform two conversions. One to first convert the tensor to a CSR temporary, and then another to convert the CSR temporary to the format that we really wanted in the first place. The result is that hand-optimized libraries significantly increase the cost of performing conversions. And as we can see, this can greatly reduce, if not completely eliminate, the performance benefits that comes from working with multiple sparse tensor formats. This then motivates the need for a compiler that can automatically generate efficient code to convert tensors between arbitrary combinations of formats. So my name is Steven, and in this talk I'll show how a compiler can do exactly that. At a high level, our idea is that instead of having developers implement complex code for every possible combination of source and target formats, we'll simply have them provide specifications that describe how to generate code for each source format and each target format individually. So to support conversions to a specific format, say dia, a programmer will have to specify how tensors can be efficiently assembled in that format. But as we'll see later, this is done in a way that's completely independent of the source format. So the same specifications can be reused to generate any conversion routine that converts the tensor to dia. In a similar way, to support conversions from dia to any other format, a programmer simply has to specify how dia tensors can be efficiently iterated. So now if a programmer provides a similar set of specifications for every supported format, then the compiler can use those specifications to generate conversion routines for any combination of those formats. And as our evaluation shows, these generated conversion routines are actually efficient. To demonstrate this, we measured the performance of code generated by our technique and compared them against two widely used sparse linear algebra libraries, namely SparseKit and MKL. The results here show average normalized execution times across a set of test tensors, so the lower the better. And as we can see, code generated by our technique has comparable if not better performance than both hand-optimized libraries. This is especially true for combinations of source and target formats that aren't directly supported by the other libraries, and this is simply because our technique can generate code to perform those conversions without requiring any CSR temporary. As such, our approach minimizes the overhead of converting tensors between arbitrary formats. This then allows users to more effectively optimize the performance of their sparse tensor applications by using different formats to optimize each individual operation. Now in the rest of this talk, I'll show how specifications that independently describe the source and target formats can be used to generate efficient tensor conversion routines. In particular, we'll first look at how a compiler can generate code to reorder stored nonzeros in memory when converting tensors between different formats. Performing such reorderings of nonzeros is an integral part of tensor conversion because different tensor formats group together and order nonzeros in very different ways. Some formats, like CSR for instance, store nonzeros in row major order. Dia, on the other hand, groups together nonzeros by diagonal, whereas the BCSR format groups together nonzeros by block. And many other formats store nonzeros in even more complex orderings, like Morton order for instance, to better exploit hardware capabilities for compute performance. So to be able to generate conversion routines for a wide range of target formats, a compiler needs to know precisely how all those target formats arrange nonzeros in memory. Now this is complicated by the fact that many formats don't actually store a tensor's nonzeros in any lexicographic order with respect to their canonical coordinates. But what we observed is that by computing additional coordinates as functions of each nonzero's canonical coordinates, we can use those additional coordinates to reorder nonzeros in different ways that reflect how formats like Dia organize nonzeros in memory. As an example, consider the matrix shown on the left here. Now we can lay out all of its nonzeros linearly, and this is how they'd be arranged if we just order them lexicographically by their canonical row and column coordinates. But now if we additionally compute each nonzero's offset as the difference between its column and row coordinates, and if we then order the nonzeros lexicographically by their offsets as well, then we see that the nonzeros are actually grouped together by diagonal. So now when we compare this ordering of nonzeros to the Dia representation of the same matrix, we see that it precisely captures how nonzeros are ordered in Dia. We can then describe how Dia organizes nonzeros using a very concise notation as shown here, which simply specifies that nonzeros are grouped together by their offsets, and that nonzeros within each diagonal are arranged by their positions along the diagonal. In our paper, we show how similar coordinate remappings can precisely specify how other tensor formats organize nonzeros using additional computed coordinates. A compiler can then use these coordinate remappings to generate code that reorders nonzeros when converting tensors between different formats. At a high level, this entails emitting code that uses computed as well as canonical coordinates to recursively locate where each nonzero should be inserted into the result. So to insert a nonzero into Dia, for instance, the generated code will first compute the nonzero's offset and use it to identify its corresponding segment in the vowels array. Then, the generated code will use the nonzero's canonical coordinates to find its position within the segment, before finally inserting the nonzero at that position. Now if we want code that converts, say, a BCSR matrix to Dia, the compiler can simply use specifications that describe how to efficiently access BCSR matrices in order to generate loops that iterate over the input. Then, if we step through this code, we can see that it iterates over the nonzeros by block, but reorders them so that they're stored by diagonal in the result. So we've just seen how a compiler can generate code to reorder a tensor's nonzeros in memory when converting it between different formats. However, reordering nonzeros efficiently often requires knowing certain statistics about the tensor beforehand. To see why this is the case, let's suppose we have the same matrix as before, but this time we'd like to convert it from the coordinate format to CSR. As we can see on the right, The coordinate format stores the matrix as a list of its nonzeros and does not have to store those nonzeros in any particular order. By contrast, CSR uses a pos array to segment the nonzeros into contiguous chunks that each corresponds to a single row of the matrix. Now, one way to perform the conversion is to simply iterate over the input matrix and one by one insert each nonzero into the result. We can insert a nonzero, say element A, into the result by copying over its column coordinate and value. But then to also keep track of the fact that A belongs in the first row of the matrix, we have to update the pos array accordingly by incrementing every element after the first one. And as we repeat this process for every input nonzero, we see that every insertion actually requires updating most elements of the pos array, which imposes significant overhead. But not only that, now we've encountered another nonzero that's also in the first row. So to ensure that all nonzeros in the same row are grouped together in the result, we actually have to insert this new nonzero in front of all other nonzeros that belong to subsequent rows. As we can see, this requires shifting all those nonzeros in memory, incurring yet more overhead. So what this demonstrates is that, without knowing anything about the input matrix beforehand, converting it to CSR is extremely inefficient, as it requires many redundant updates of the pos array, as well as constant reshuffling of nonzeros. However, if we had known exactly how many nonzeros are in each row of the input matrix, then we could have actually constructed the pos array in one shot by just performing a prefix sum. This effectively pre-segments the coordinate vowels arrays, at which point converting the matrix to CSR would then simply entail appending each nonzero to the end of its corresponding segment. As you can see, this can be done without ever having to touch another nonzero that's already been inserted. So we've just seen how knowing the number of nonzeros in each row of the input matrix speeds up conversions to CSR. It turns out though that efficiently converting to different formats actually requires knowing different statistics about the input tensor. Converting a matrix to the skyline format, for instance, which is useful for sparse solvers, requires knowing what the first nonzero of each column or row is. Other target formats, meanwhile, require knowing even more complex statistics about the input tensor, such as its upper and lower bandwidths, for instance, or even the exact set of non-empty diagonals in the tensor. And furthermore, as we'll see shortly, computing any one of these statistics for a tensor can require very different code depending on what format the tensor is originally stored in. So in order to support converting tensors between arbitrary source and target formats, a compiler must be able to generate efficient code that can compute these kinds of statistics for inputs that are in arbitrary formats. This requires us to be able to precisely specify what statistics are needed in order to accelerate conversions to the desired target format. But such a specification also has to be sufficiently high level so that the compiler can lower these specifications to code that's optimized for the intended source formats. What we found is that a wide range of tensor statistics can actually be expressed in a declarative manner as attribute queries that simply aggregate the coordinates of nonzeros. For instance, to express computation that returns the number of nonzeros in each row of a matrix, we can simply define an attribute query as shown on the right, which for every distinct row with coordinate I counts the number of unique non-empty columns in row I. But in fact, for any matrix, each column in a row actually corresponds to exactly one element. And so if we apply this query to the matrix on the left, and then look at the results for any row, we can see that the query actually returns a number of nonzeros in that particular row. This demonstrates how statistics that are required for efficiently converting a matrix to CSR can be specified declaratively. And in our paper, we show how different tensor statistics that are required for other target formats, like the ones we saw before, for instance, can be similarly expressed as attribute queries. All we need now then is some technique that can generate efficient code to actually compute these attribute queries for input tensors that are stored in arbitrary source formats. Fortunately, it turns out that any attribute query can in fact be mechanically lowered to some equivalent sparse tensor algebra expression that computes the same result. Here we see, for instance, how a query that computes the number of nonzeros in each row of a matrix can be lowered to the expression shown on the right. At a high level, this expression first takes the input matrix and maps every nonzero to the constant 1. Then, simply by summing up each row of the transformed matrix, the expression computes the number of nonzeros in each row of the original matrix as desired. So now that we've lowered the attribute query to sparse tensor algebra, we can directly leverage prior work we presented on generating efficient sparse tensor algebra kernels in order to generate efficient code for computing the attribute query. Let's say, for instance, that the input matrix B is stored in the CSC format. The Taco compiler, which implements our prior work, can then generate efficient code to compute the query by first inlining specifications that describe how to efficiently iterate over a CSC matrix, and then within those loops, emitting code to count each input non-zero. On the other hand, if B is instead stored in the Corna format, then Taco can apply the exact same procedure, but this time using specifications that describe efficient iteration over a Corna matrix, in order to generate code that efficiently computes the same query for Corna matrices. And furthermore, for certain source formats, our compiler can actually optimize the query further by applying semantic preserving transformations to the lowered expression before invoking Taco. So for instance, if B is stored in CSR, then our compiler can actually rewrite the expression by having elements of the result be computed as differences between adjacent elements of the pos array. This yields code that avoids having to iterate over the non-zeros, which minimizes memory traffic at runtime. In this way, our technique can take the same attribute query and generate efficient code to compute it that are optimized for disparate source tensor formats. So in summary, we've seen how a compiler can generate code to efficiently convert sparse tensors between disparate formats. And a compiler can do this given only specifications that describe how to efficiently construct and iterate over tensors in those same formats. Furthermore, these specifications are simple to provide, so it's easy for users to extend our technique to support even more tensor formats without having to modify the compiler itself. Our technique thus makes it much easier for users to optimize their sparse tensor algebra applications by fully taking advantage of all those sparse tensor formats that have and will continue to be developed.